I want to just do a quick video here of example that was in the book, and so I printed it out here. I just think this is a good example, and this won't take very long. Basically, this is giving us the velocity graph of a particle moving along a horizontal line. So it's kind of like the cubic equation earlier, but it's much more complicated, right? The other thing is that this is the graph of the velocity. You got to remember this. This is the graph of the velocity, not the position. Okay? And so what can we tell about the position? Okay? Well, first, don't make the mistake. Don't think like this thing is starting at 0 and going in the positive direction and so on, okay? Because this is the speed, okay? So one of the main things you can see, you have these 3 divisions, or you have kind of 4 divisions here. This is where the particle is moving forward to the right. And why is that? Because the velocity is positive. It's above the x-axis. Now, the particle or whatever is moving backwards. Why? Because the velocity is negative, okay? Now here, the velocity is 0, okay? And so the particle is standing still at this point. We don't know where it's at, but it's not moving. The velocity is 0. And then here, it speeds up again and it's going forward, okay? And so then it further divides. You got those 3 categories. Now it further, or those 4 categories, now it further divides them up here. And it's like from here to here, this particle is like speeding up. So at this point, the velocity is 0. It's not moving, and it speeds up until it reaches some point, and then it just goes at a constant rate. So the particle is still moving in the positive direction, but it's not speeding up. It's kind of like you're accelerating to 60 miles per hour, and then you're going for a distance 60 miles an hour. But then it slows down. It slows back down to 0. Okay? And then now this is in the negative direction, and this is more, again, it speeds up and then slows down. So this doesn't have that constant in between the two. It just kind of speeds up to a maximum velocity, or in this case a minimum velocity. It speeds up, but it's speeding up in the negative direction. So a negative higher speed is a maximum velocity, or a minimum velocity, not a maximum. But it is a maximum speed in the negative direction. And then it goes back down. Now it's slowing back down. And then once it hits here, it's kind of stopped. Wherever it was at, it's just not moving. And then it kind of goes back in the other direction, and it's increasing at a constant rate. Okay? So this thing, the path, or the actual graph would look like a parabola. I mean, the path is a straight line, but the rate, this is a line, and you get like a parabola for the actual position function. But here it's speeding up, okay? Because the velocity is greater than 0. So you could try to graph this. I don't know, we could give it a try, I guess. I wasn't sure if I wanted to do that. But I could kind of try to make a graph here for this. So you kind of have this, and you got like, and it doesn't matter where you start, because remember, there could be an infinite number of position functions, all vertically translated up and down, that would give you the same velocity. So I don't know, we'll just start here. We won't start at 0 because you don't have to start at 0. So now it's moving in the positive direction, and it's speeding up. So this is so it's kind of speeding up like this, but then it reaches, it's like a constant rate. And so this here is kind of your 1 and 2, right? This is like a constant rate, and then it's slowing down, but it's not like going it's not going backwards yet until it reaches 3 here. And now it's going to go backwards. But this down here doesn't mean it's going to go necessarily on the other side of 0, right? So it's just going to be going backwards, and it's going to increase its speed. And this is like 2, so this is 3, 4, and 5. And at 4, you have this inflection point. So this is going to be kind of going like this, but then it's going to change its concavity. So you get this inflection point, and it'll change like its concavity like this. So again, it doesn't even necessarily have to get down to 0, but the thing is, it's going to be 0, and then it just for it looks like for a minute, it just stops there. It doesn't move at all. And then it's going to speed up again at a constant rate, kind of like as a parabola. So it would be like this, and then this point, that's the hardest one. It's where you go from concave down to concave up. And this is an inflection point. And in particular, an inflection point is the second derivative, the acceleration is 0. Because, see, you get a horizontal tangent, so if you take the acceleration, you get 0. But for the actual position, the inflection point is when it changes its concavity, like that. So this might be the way that would look there. So, assuming that this isn't perfect, but this should have been completely constant at that point. So, okay, so that kind of gives you an idea then about the relationships of these graphs. This is starting with a velocity and then getting the position, right? This is like your s of t, in other words. And this is your t. And so, and notice I could have started this down here and done the whole thing down here. It doesn't matter where it's at vertically. Okay, you can translate it up and down. The derivative is going to be the same because the constant just goes away. And another way of thinking about it is the slopes of these. So like at 3, you got a horizontal tangent right there. At 5, you have a horizontal tangent, and it's actually horizontal kind of at 6, kind of over that whole thing. Okay, but that's if this thing shifts up and down, those slopes at any given point aren't going to change.